So the main point of my talk is to hopefully get you to agree or disagree, to make you think about this idea. If AI for Earth or AI brings a whole new paradigm, a whole new way of doing geo. So please put your questions if you are live, and if you are watching this in YouTube, put it on YouTube. I will do my best to read all of them and respond. At the end of the day, what I believe most people in geo are doing is to answer this question: what is where at scale? What is on Earth? Where are the trees in the world? Where are fires happening? Where are floods happening? How many trees are being cut in this place or that place? And I would say that in a large extent, we have enough data to not be the bottleneck. We have enough open data, Sentinel and Landsat and others. So it's kind of solved in that way. At least it's not hindering progress, in my opinion. We also have a lot of tools which seem to solve our problem. But I would try to argue that we are not really doing as well as we are doing, and AI could be the way to do this. And the reason that this is a struggle is because I think there's no doubt that we are not having the Earth awareness that one would assume with the data that we have. We are, after all, gathering data from the entire world every few days, only counting open data. So how is it that the most basic questions are not being answered if we have data and we seem to think that we have tools? And I think at the end of the day, is because for most people, the perceived cost, like in dollars or in effort or in skills or in employees of doing Earth awareness exceeds the perceived benefits. Like, you can cut this statement into many ways, but just look at how fewer or none geospatial experts are being employed in companies that have an intrinsic geospatial function, like from logistics, supermarkets, one would assume that we need more people working on this, but we don't. And I think it's really hard to explain this because our brains are really good at the most difficult parts of geo. And I'll put an example. If I put this image, your brains instantly and immediately recognize patterns, recognize things, pull crops of wheat. It even takes me much more time to say those words, to convey that awareness into words, right? And the reason is that those things that our brains are really good at, we have to code them for geospatial. So if you go to Google Maps and you search for grass, you can see grass instantly. This is close to my house here in Copenhagen. And if you search for grass, because I know you want to take your kid there, Google Maps says there's no grass here. And the reason, those of us who know how geospatial works, is because Google Maps doesn't see this image. They see this image, the vector ones. And if you happen to have a label of that thing, then yes, you will see the results. But if it is not aware of the semantics in general. That's why in geo, we have to do most things end to end. You want to do deforestation, you have to start from the data, do the processing. Do you want to do something similar? You have to start from scratch again, do the processing. So we kind of redo the thing over and over again. But things are getting better. What used to take a lot of years and a lot of millions of dollars now takes less and less time. The progress is clear in that sense. So where are we going and how can we get there faster? Is AI the solution? Obviously, if we are here, it's because I think that is the case. And I think that is the case because geo represents a way to do things way faster, orders of magnitude faster, way simpler, orders of magnitude simpler in terms of time, in terms of dollars, and better. Not just the same, but better. And also, I would say that this vertical, AI for Earth, does not have a leader yet, or a strong leader. There are people doing really great work, but it has not become the standard, as you might imagine. So what has AI done? What can AI do? This is just a quick review of areas. This is not new to this audience. In text, audio, images, health, robots, banks, agriculture, it has shown orders of magnitude faster, better, and cheaper to do these things. But if you pay attention, we might see that in those cases, most cases, you can do exactly that with transformers, the T in ChatGPT. it seems that transformer has been a human invention that is able to capture a lot of semantics. So then it begs the question, what about Earth? What about Earth that we can apply with this revolution of transformers, which I would pose that has not happened at the scale that could happen. So first of all, we have to also say that what has happened on Earth with AI is that it has taken the cost in many ways. The cost of doing transformers, because it's very data hungry, is a lot of emissions, a lot of electricity, a lot of water. So let's not forget about that. And ways to do that are extremely important, because even though the major clouds, all of the major clouds had plans to reduce emissions, because largely to AI, those expectations are not being met, and indeed we are doing more and more emissions. And I know that very well because I used to work with one of these clouds with Microsoft, and I was exactly in the team doing this planning. And it was not lack of trying and lack of effort to do these things. So AI for Earth then becomes the obvious underdog, because we have the data, as I said, we have the compute, I think is less demanding. We can argue about that in the Q&A. There is fewer legal blockers, because there's a lot of open data without any problems of licensing or attribution of or human-made data that you would need to figure out how to pay back the creators. I think there's a clear market, a clear traction to understand Earth, and there is nothing there yet, or not really a lot done in that sense. Let me also add that the concept that is very well known in development of AI, of digital dividends, which is the concept that when the world became digitized by using mobile phones or by using internet or by using other technologies, it has shaped progress in many ways. And there is this very studied concept of digital dividends, like, for example, the World Bank report. And I would pose that there's going to be a talk more and more on AI dividends, especially in the context of development, because AI seems to be, again, much faster and much more unequal, bringing those dividends. And one of the key learnings of the digital dividends is that the earlier you jump on the other side of the gap, the better it is because of the compounded effect. We can talk more about those and just throw in a few pointers to drive, hopefully, people to think about this. You can see the slides at your own pace. I put the link in the first page. And I think at the core of all these problems, and this is the main part, is that we seem to think we have a technology problem, where I think we have a product problem. We love our complexity in geospatial. It is very complex, and we find ways to make it even more complex and mature the complexity so that to make sure that it's guaranteed to work in all cases. But our products are really bad. They are really ugly for engineers, and we seem to wait for the world to embrace geospatial, where I think we should do the opposite and bring geospatial to the world by removing complexity. I love this image of the evolutions of the rocket engine that is progressing by reducing complexity. There is this couple of quotes of the mentality that seems to dominate most of geo, most of tech, and most of science also, of the free play of the free intellect, which is important. We have to have those. But then at some point, you also need to ask the questions like the lawyer Fran Biso asked in the US Capitol. At some point, with all that science, with all that technology, at some point, you need to save a life. You need to show me how this impacts. And I think that gap has not been covered because it seems to be less important for most of the technology we do. Not for lack of morals or not for lack of trying. It's just that I think we are too deep in our ways because of this plot that I already shown, because the need to redo the entire thing every time, that brings a lot of complexity. These are real workflows of some papers doing geospatial basic stuff like crop yields or things like that. What ends up being the current state of affairs for geospatial is that every single time we have the data, we have the pixels and the labels, and we do a lot of pixel math and NDVI and edge detection and clustering and CNNs and dimensionality reduction, all of those things we love to do land cover or to do land use or to do flood detection. We have to repeat the process over and over and over again, where I think the AI for Earth opportunity is to simplify all of this. Simplify that, how? with foundational models, with the idea that an AI model, a transformer, is able to front load a lot of the common computation. Like, you need to understand corners and pixel values every single time. If you are able to front load all of that processing to end up with semantics, to end up with something that is much closer to the specificity that you're looking for, then you not only remove a lot of the work for every single time, you want to do it once, but also reduce a lot of the cost, a lot of the time, a lot of the skills that the end user needs to do to deliver the same or better result. To give a little bit of example on this idea is that a lot of these models, they take an image, they convert it into a summary, an embedding, which is the semantic representation, the mathematical representation of the features there, and then the whole job they have is to reconstruct the image and then figure out how that the construction looks like the input. So that way, we have an encoder that creates those summaries, those embeddings. So what I'm saying at the end is that this image is when we redo the whole thing every single time, but if we instead do embeddings, we can simplify a lot. We do once the data to the embeddings. We use tools to work on the embeddings, doing random forest, for example, or other kinds of clustering or regressions on those. And we do the same products, or many of the same products, like object detections or others. If this is true, or to the extent that this is true, it removes 99% of the complexity, of the cost, of the time. So it's worth doing that. And some of the tools that we need for doing that is exactly things like Voxel 51, which already work on the embeddings space. Can we add regressors here? Can we add classifiers here to make that vision reality? So lastly, talk is cheap. So what are we doing about it? We thought about this for long, and we decided to create a nonprofit to make this idea, or one of these ideas, a model, an open, 100% open source, open data, open license model to do that. And we decided only to do it if we had enough budget. We were able to raise $5 million. So we designed a model that is extremely mission-driven and is not really that interested in the research aspect of it, not because it's bad, but because we want to align to the end, to the user, to the impact. So we are agnostic on the instrument, we are agnostic of the kind of data. We try to work as close to the operations as possible. It is still a technical thing. It's not the complete product, but we hope it can replace a lot of the geostack. We also designed it weirdly in the way that it has 0 employees. I don't want to worry about bringing salaries to pay salaries. I want this to be a vehicle of turning philanthropy money into common value, the entirety of it. We will hire people when we have the funds, and when we don't, it just stays dormant in that sense. Super quickly, Clay 1.5 trained on 70 million satellite images from NAPE, Landsat, Sentinel, MODIS, Sentinel-1 and 2. I think I forget others. You can see the details there. Resolutions from very low to very high, trained on something like 16,000 hours, GPU hours on AWS. The models, the architecture is here. It's basically a visual transformer where we add the geospatial stuff, and we also force the model to work consistently regardless of what instrument you are giving it. But also we force the model to understand Earth itself. By removing 10% of the time, we remove the entire raster, and we only give it the location and the time and the instrument to try to reconstruct the thing so that the model can understand Earth itself. I'm happy to go into details why we made those choices, but we believe these are the sweet spot between flexibility and pragmatism of use. You are familiar with these plots of embedding, so I will not dwell. I will only end with some results that we are seeing more than 92% reconstruction of biomasses with regression of embeddings. Of course, of embeddings I had not seen, so not part of the testing of the test set. And also in land use, land classification, same thing, around 90% for most classes of land type. We have other tests of this. Happy to spend more on the Q&A, but I don't want to take too much time from from Steve and Mikkel. We have also real examples of companies who are using this and are turning what used to take $55,000 and 1,000 full-time equivalents now to $400 and 21 full-time equivalents to do the same product, which is extremely, extremely exciting to see that work. Finally, if you want to take a look how this kind of product might look like, not the technical part, but the end user experience, you can go to explore.madewithclay.org, where we have a little demo of how similarity search works. So Jimmy, back to you with this a little bit fast-paced question of, can we reimagine the geospatial stack?
Fantastic. So we do have 3 questions, and the context on the first question was right before you started doing an introduction to clay slides. So it was right before that particular slide. The question was, how do you think this gap should be covered or can be covered? So it's a bit out of context in regards to, I don't know exactly.
The gap of,
go ahead.
Say that again, the gap of what?
I think, how do you think the gap should be covered or can be covered? So there's not a lot of context here, but it was right before your intro to clay slide. Perhaps Ritka.
Yeah, okay. So yeah, that's when I turn into talk is cheap. How can we cover things like clay? There's also other models like NASA Prepfee. There's other models, and I hope other models come. And I did make a prediction in SAT Summit a few months ago that I don't think it matters much. Like, the goal of clay is to either become the standard or become irrelevant. And what I mean by that is that I have reasons to believe that AI models of Earth will train much faster and much better than text models, to the point that at some maturity, it won't really matter if it's clay or Prepfee or others. They will give pretty much the same result. There's a last mile of maybe 10% accuracy that might matter to some people, and that's really important, and we can do fine tuning. And there's a whole market, I believe, commercial market for that last 10%. But for the large extent, the gap will be covered by these models.
Fantastic. So the next question came right when you started your introduction to clay slides. Can you elaborate a little on what sort of transformer-based architectures are relevant for Earth data?
I think the classical visual transformer conveys already most of it, and we've seen it used, for example, for weather prediction, what is also with the atmosphere, which when we say AI for Earth, in our case, is the land, but with some specific tweaks, like the geospatial, the location in space and time, and also through which wavelength or through which instrument, because we are kind of imaging the same thing, maybe in infrared or visual. But that's what I think context or attention means for Earth transformers.
So the next question came right when you started to introduce your idea around a new geospatial stack. And the question was, could you talk a bit more about the types of input data currently used to train the model and how that may change in the future, particularly in terms of sensor resolutions, modalities, and input metadata?
When we started Clay, we used to think that the name of the game would be to make a foundational model self-supervised, where you try to reconstruct the input image, so you don't need labels. It needs to reconstruct the input image going through a bottleneck of an embedding. And that's enough to teach a lot of semantics. And then you use labels of crops or whatever thing it is as the fine-tuning example. I am more and more convinced that that is a different view. I am more and more convinced that you just do self-supervised, and then the fine-tuning or the use of the specific labels is just an embedding inference time, like a random forest or cosine similarity or stuff like that. So the labels come at the very, very back end. You don't use them in foundational models, which means also that these embeddings become universal.
And we'll take 2 last questions, and the rest we'll take offline. Our next question is there any more information on how the imagery and labels were prepared to create the geo embeddings for training a biomass regression model?
Okay, so for the first part, all of that works is in the repo. You can take a look to that, who created the chips of that. For the biomass, what we did is we collaborated with a nonprofit called C-Trees, where they calculate biomass with other physical models. So we did it for California, so we took the entire state of California, and they had a label they made with their estimates of biomass. and we used those as labels, and we took the chips of Sentinel, whatever thing, I think it was Sentinel-2 chips of that location and the label they gave us, and we used 80% of those as the training set. So we in this case, we did fine-tune the model to, no, actually we didn't, we did embeddings, yes. So we took the embeddings of those locations and we did a random forest to regression to that, to that biomass. We tested with 10%, and the remaining 10% is the ones that we used for the plot user.
Fantastic. So I lied. We'll actually take two last questions. I think the last question is actually interesting that just came in. Our next question is, can you share your experience with data collection, particularly from open data platforms? Did you find the process centralized and user-friendly?
For the extent of creating clay, we only use satellite data. So we actually used exclusively AWS public datasets for figuring out the pixels, the data sources, the rasters, all of that stuff. But we could have used Planetary Computer, which has the same data, or other places. For the applications of the labels for testing the land use, land cover that you saw in one slide, or the biomass, for the biomass, it was labels given by C-trees. And for the land use, land cover, we used Sentinel ESA's land cover maps. To do that, we also did some testing for retrieving labels from OpenStreetMap, and it changes a lot the quality of that retrieval. Precision seems to be better than recall, and there are good reasons for that.
And then our last question that came in from Christina, and then we'll take the rest of the questions offline, is, can you please elaborate on space and time? Will this be able to identify real-time locations of people and things?
If you have the data, yes. The idea is that I don't think about time. Well, I do embeddings for every single time. So if you're looking for time evolution, you do embeddings for every single time, and then you see how those embeddings move in the embeddings space. If you have real-time data, you can do real-time. It takes roughly milliseconds on a GPU to do inference of those embeddings, and roughly depends on the CPU, but something like 5 seconds to do the inference. So of course it takes more time, unless you run clay on, I don't know, a plane or a satellite itself. It takes time to reach the GPU, and once it's there, it takes from milliseconds to seconds to do that, and then you can do whatever you want to do with it.
Fantastic. Well, I appreciate everybody asking all the questions. That's all the time that we have for questions for Dr. Nuno, but we'll either allow him to answer those questions in the Q&A, or we will definitely take those questions offline, forward them, and get them answered and include them in the follow-up post. So if you have any closing comments, Dr. Nuno, we will then otherwise jump over to Michael.
No more questions. What Michael is going to present us is a perfect example of how AI can revolutionize. So I'm very much looking forward hearing you, Michael.